All right, at this point, we've solved exponential equations. We've solved log equations, and one of the things that's been kind of consistent throughout all of this is the bases. Now, the bases for the logs or for the exponents, they've always been the same, or at least we were able to get them to be the same. So this last lesson we're going to be doing on solving is what if the bases aren't? What if we're not able to get the bases to be the same? What if one base is 7 and the other one is 2? I mean, you really can't get those to equal each other. So we're going to go through that process and how we handle that here. So this is solving exponential equations using logs. So we're going to kind of be using both together. So this is, again, the issue that we're going to have here is these bases. Like you look at example number 2. I can't get the right-hand side to equal a base e. That's not going to happen. So anyway, what happens when we have that situation where we can't get the bases equal? So what we're going to do, number 1, is we are going to isolate the exponential expression. Once we get it isolated, which means every other number is moved to the other side, then we take the log of both sides. And that's just like dividing both sides by a number, or adding both sides by a number, or dividing. You're doing the same thing to both sides, just algebra. We're doing with a logarithm. And then we're going to expand the logs using that power rule. That power rule is going to be super important for what we're doing today. And then we're going to solve, and as always, check for extraneous solutions. So here we go. We're going to start on number 2. Number 2 has e to the x equals 140. I was mentioning that anyway, so let's go ahead and do it. Now, in this scenario, what we have is we have a situation where we have an exponential equation. If you review when we were doing exponential equations, the goal is to try to get the bases equal to each other so I can use that one-to-one property. But I can't get the right-hand side to have a base of e. So what we do instead, notice step 1 is already done. The exponent is already isolated. I'm going to take the log of both sides. Now you have 2 logs that we're going to potentially take. We can actually take multiple logs, but in this case we have a log base e. So I'm going to take a natural log of both sides. So I'm going to do natural log of e to the x equals the natural log of 140. Now the reason why I'm doing natural log is because of what happens after this step. First thing what we'll do is we're going to undo that power rule, which means I'm going to take this x, I'm going to move it out front. That's the power rule. So that's going to be x times the natural log of e equals the natural log of 140. And here's what's really nice about this. The natural log of e, if I tried to solve that, what I would do is I would put an e on the bottom because that's the base of the natural log. You'd have e to the y equals e. So e to the y equals e, we get y equals 1. So what that means is the natural log of e is 1. In other words, it cancels out. So I end up with x equals the natural log of 140. So you can write that as a natural log of 140 if you want. You can also plug it into your calculator and get a decimal version of that answer. So natural log of 140 is going to be 4.941. So either one, mostly decimals though. But anyway, that's going to be number 2. That's basically what we're doing here. Now, sometimes you're not going to have base e, and that's okay. So let's say I had something that wasn't a base e, and we can handle it either way we want. But we have mostly 2 choices to choose from, either common log or natural log. In a way, I prefer natural log. I know a lot of students at first do like common logs. But anyway, we have a situation here where we have a base that's not 10 or e. But we approach it really the same way. So here I'm going to do one more natural log here. I'm going to natural log both sides. So I have natural log of 1/3. This will write, there we go. 1/3 to the 2x minus 5 equals the natural log of 120. So I'm using natural log. It doesn't matter which log you use. That's why I say I just prefer to use natural log anyway, but I'll go back and forth with which ones I end up using. So here I'm going to use that power rule. I'm going to pull that out front. So it's going to be 2x minus 5 times the natural log of 1/3. This just adds a couple of more steps to my problem. Those steps just include me dividing both sides by the natural log of 1/3. Again, think about it this way. I'm trying to solve for x. So in order to do that, I got to get rid of everything else that includes that natural log. So I'm going to divide that on both sides. Now for right now, I'm going to keep that quotient the way it is. You can write as a decimal if you want. You just have to make sure you're storing that number as you go through the problem. So I'm just going to leave it as is right now. So right now I have 2x minus 5 equals that natural log. And now I'm going to just add 5 to both sides. So that's 2x equals that natural log plus 5. And then I'm going to divide all that by 2. You're going to need a calculator for this at this point, but at least I don't need to store numbers. And it's up to you if you want to store numbers, it's okay. So anyway, here I go. I'm going to go natural log of 120 divided by natural log of 1/3 plus 5. I'm doing it in little parts as you can see in my calculator. I'm going to divide that by 2. And there we go. So x is approximately 0.32, I'll say 321, and that would be just fine and dandy. So again, in all these we're saying, we have a scenario where we have logs, you want to check for extraneous solutions. That's not really going to be an issue here. I mean, the only issue is if you have like a situation where your logarithm would be negative, but we have numbers here, so we don't have to worry about that. So in this case, we are good to go. If I plug in 0.321, I don't have any extraneous solutions in this case. So that's going to be number 4. I'm going to jump down to some of these harder ones at the end here so we can see what some of the trickier ones may look like. Like we have 2 exponents. So before I get to that, let's do number 8, and then I'm going to finish up with the ones that have 2 exponential equations at once. So number 8, what we want to do is, again, in this scenario, we want to isolate the exponent so I can log both sides. Again, that's our general process as we've always been doing. So on these first two, so I'm going to subtract 9. I'm trying to isolate the exponent. So I have -2 times my 4 to the 2x plus 7. And that's going to equal -55 minus 9, so -64. And then I'm going to divide both sides by -2. And now I have my exponent by itself. Okay. So in this case, I'm going to go ahead and log both sides. Now, in this case, you may know if you're on a test, you might want to see like, oh, the 32, maybe I can break that into 4s, but you can't. You could potentially break it into 2s. So I just want to remind you that this would be 8 times 4, and that's 2 times 2 times 2, and that's 2 times 2. So in a situation like this, remember, if you can break the bases down so that they're equal, feel free to do that because this would still work. So if I did this, this would be, 4 is 2 times 2, so this would be 2 squared raised to the 2x plus 7. So if I was going to solve it this way, I'd have 2 to the 4x plus 14 equals 2 to the 5th. So if I'm going to solve this, all I would do is use that one-to-one property. I'd have 4x plus 14 equals 5. And then when you solve, you get 4x. Again, I'm subtracting 14 from both sides, so that's -9. So x would be -9/4. And again, if you can get those bases to be the same, it works, okay? But if you can't, you should, or even if you could, like I said, in this situation, I'm going to show you both ways, it was going to work either way. So if I came over here and I didn't see that, but say I had a calculator where I was able to solve this with a calculator, you can then take the log of 4, because I'm going to try some common bases here, it doesn't matter, of 2x plus 7 equals a log of 32. So if I pull the log, the power out front, I get 2x plus 7 times the log of 4 equals a log of 32. And now I'm going to do a little bit of algebra here. I have 2x plus 7 equals log 32 over log 4. I'm going to subtract 7 from both sides. So that's -7, and then I'm going to divide everything by 2. So again, you'll notice it actually looks like a little bit more work. I mean, it depends on how long it takes you, but I'm going to go ahead and do that math. So this is going to be log of 32 divided by log of 4 minus 7 divided by 2. And again, if you go math fraction here, you're going to see we get negative 9/4. It's the same answer. So it should be the same answer, I mean, obviously. But like I say, sometimes you're able to do that by hand, but sometimes you're not. In this case, you were able to do it by hand, but I'm just kind of showing you both ways. But now, what if we have two exponents? All right, so now we're going to move on to problems that have two exponents in them. So as we approach these, we're going to start them in a similar way we solve problems with a single exponent. As long as these exponents are isolated here, we can go ahead and log both sides. So that's what we're going to do on this. We're going to log both sides to begin. And again, you can either pick common log or natural log. It doesn't matter which one. So I'm just going to go natural log, and then I'll do common log in the last one. So I'm going to go natural log of 8 to the 2x minus 1 equals natural log of 5 to the x plus 3. And then we're going to pull those exponents out front. So this is going to be 2x minus 1 times the natural log of 8 equals x plus 3 times the natural log of 5. Now, in order to solve this, we are going to need to get the exponents, not the exponents, the variables, sorry, on the same side of the equation. I can't just subtract x right now because it's being multiplied by a natural log. Same thing with this 2x if I want to move it to the right-hand side. So we're going to need to multiply out those natural logs. Get rid of we're going to need to distribute, get rid of the parentheses. So I'm going to go ahead and do that first, and you'll see what we're doing with this once we get it all multiplied out. But we're going to multiply out that natural log of 8 on the left-hand side. On the right-hand side, we get x natural log of 5 plus 3 natural log of 5. So now I can get my x's on one side, I can get my constants on the other. So I'm going to move my x's to one side of the equation. So that's going to be 2x natural log of 8 minus x natural log of 5. I'm going to take the natural log of 8 and add that to the other side of the equation. So that's going to equal 3 natural log of 5 plus the natural log of 8. Now I'm on my left-hand side again. I'm going to look at that those two terms. I see there's a GCF. That GCF is going to be x. That's really our main goal, is to get that x by itself. So I'm able to do that by factoring that x out of that equation. So that becomes 2 natural log 8 minus natural log 5. On the right-hand side, I still have this log. Now what I'm going to start to do in these next couple steps, I'm going to rewrite this as natural log of 5 cubed plus natural log of 8, because what I'm able to do is I'm condense these logs as I start to try to solve for x. So over here this will be 8 squared, so I'm going to have x times the natural log, and since I'm subtracting, I'm going to condense this as one logarithm. It's going to be 8 squared, so 64 divided by 5. That's me condensing using my quotient property and my power property there on the left-hand side. On the right-hand side, I have the natural log, and if you don't see what this is going to equal, 5 cubed is 125, but we're multiplying that by 8. So you have 5 cubed times 8, so I'm going to get 1,000 over here. So natural log of 1,000, because I'm multiplying those two inputs together because of the product property. So now when I divide, I'm going to get the natural log of 64/5. I'm going to divide that on both sides, plug that into our calculator, and let's see what we get. So this again becomes the natural log 1,000 divided by the natural log of 64/5. And we're going to get about 2.7095. And there we go. Otherwise, there's really not much going on here. You see there's a few more steps on these. We get to apply all our properties, which is really good. But that's solving with two exponents. We're going to wrap up with one more. So we're going to look at number 12 here. So number 12, I'm going to do common log. Again, it doesn't really matter. Let's just pick one and go. So this one is going to be common log of 9 to the negative 2x equals common log of 2 to the 5x plus 4. Again, pull out those exponents. We have negative 2x log of 9 equals 5x plus 4 times log of 2. So again, on this one, remember we want to get the x's on one side of the equation. In order to do that, I am going to need to distribute that log first. So I copy down the left-hand side, and that's going to equal 5x log 2 plus 4 log 2. Now I'm able to, again, get my logs on one side of the equation. So when I do that, I'm going to move this log over here to the left-hand side. So that's going to be negative 2x log 9 minus 5x log 2 equals 4 log 2, or a constant on the other side. So now we're going to start using some properties and some factoring here. I'm going to pull out a negative x. It makes it look a little easier at this point. I can divide by negative 1 when I'm done, but this is going to be now just 2 log 9 plus 5 log 2. On the right hand side, I'm going to go ahead and write this as the log of 2 to the 4th, just so you can see that. So over here, the 2 comes to the top. I'm using some properties now of logs, so that's going to be log of 81, so 9 squared. Over here, that becomes 2 to the 5th, which is 32, so plus log of 32. And then 2 to the 4th, that's going to be 16, so this is log of 16. So before I finish combining these, I do want to make sure I get 81 times 32 correct. So I'm just going to go 81 times 32. When I combine these, that's 2,592. So this is negative x times the log of 2,592 equals log 16. And now I'm able to solve here. I'm going to divide these two. This is going to be log 16 divided by log of 2,592. When I divide those, let's see what happens. So log 16 divided by log 2,592. Again, note this is going to be negative x equals that number. So I'm just going to go ahead and basically divide that by negative 1 now. And you finally end up with x is approximately negative 0.3527. So that is solving log equations. Again, that's about as nasty as they'll get. So as long as you get that, we should be good to go.